Hi students, today we are going to discuss three different cases under damped oscillations. What are the three different cases? The first one is overdamping, and the second one critical damping, and the third one is underdamping. So these three conditions arise from the general solution of the damped oscillation. The general solution of the damped oscillation is given by x is equal to x naught by 2 into 1 plus b by square root of b square minus omega square and e power minus b plus square root of b square minus omega square into t plus x naught by 2 into 1 minus b by square root of b square minus omega square into e power minus b minus square root of b square minus omega square into t. So in this equation there are two parameters. The one, the resistive force B, the another one, the frequency of the oscillating system omega. So these two, resistive force and also the frequency of oscillating system, are connected with the factor square root of b square minus omega square. So how this resistive system leads the frequency of the oscillating body, and resistive system is equal to the frequency of oscillating system, and the resistive system lacks the frequency of oscillating body. So by considering these two factors, we are going to arrive three different equations or three different conditions, that is one for the overdamping condition, another one for critical damping, and another one for underdamping. Right? So we will go one by one. The overdamping condition is that the b square is greater than omega square. So if b square is greater than omega square, so square root of b square minus omega square is less than b. So what happens here? The resistive force is very high. That is, b square minus omega square is very less. So that means what? The object immediately reaches the rest position. It is not reaching the equilibrium position. You be clear that. So when you consider x-axis, y-axis of the oscillating system, the x-axis is time and y-axis is displacement. So suppose the body initially starts from the maximum displacement. If the body is released, then the system suddenly comes to the rest position, that is, b is greater than omega. So since the body do not oscillate, then the x value is now need to determine. So the underdamping condition is nothing but this is referred as a overdamped or deadbeat or aperiodic motion. So in this motion, the body suddenly reaches the rest position. So after passing through its maximum displacement, simply slumps to its equilibrium position and the rest there. So the body do not move from this point, it rests at that point. It ceases to vibrate anymore. So further the body will not vibrate at all. Those type of condition, that is b square is greater than omega square, will be considered as a overdamping condition. Otherwise we call it as a deadbeat condition. Next we will move on to the critical damping. So in critical damping is that when b square is equal to omega square, that is, the resistive force is equivalent to the frequency of the vibrating system. So here this pictorial representation of three different cases: overdamping, critical damping, and underdamping. So the overdamping is nothing but from the maximum displacement, it just rests to the equilibrium position, or sometimes it rests here itself. So this will be called as a overdamping. Critical damping is the one which passes through the equilibrium position, but it does not oscillate for a long time. The oscillation ceases very fastly and comes to the equilibrium position. That will be called as a critical damping. And the underdamping condition is that the body will be oscillating for a while, for a time period t. So when the body is oscillating, what about the amplitude of oscillation? It slowly diminishes to 0. So it diminishes with the factor of e power minus t. It diminishes with the factor of e power minus t. Since this is your t and this is your displacement d, it diminishes with the factor of e power minus t. That coefficient we have to determine. Okay, is it clear? So we will see critical damping. So this is the general solution of the damped oscillation. So this is the general solution of damped oscillation. So in this case, critical damping B square is equal to omega square. So we can't take B square is equal to 0. So what happens when B square is equal to 0? The second term completely becomes 0. So it does not have any significance to derive the equation for critical damping. So for what we are going to do is square root of B square minus omega square will be considered as to be a very small quantity epsilon. So very small quantity epsilon. So I am going to replace this square root of B square minus omega square with respect to epsilon. So this general equation comes x is equal to c e power minus b plus epsilon into t plus d e power minus b minus epsilon into t. So here e power bt, this e power bt in the first term, e power bt in the second term is taken as a common outside. So you will be getting e power minus bt, c e power minus epsilon t and d e power minus epsilon t. So c e power epsilon t plus d e power minus epsilon t will be within the bracket. So once again, this e power epsilon t will be solved with the approximation equation. E power alpha t is equal to 1 plus epsilon t. So e power minus epsilon t will become 1 minus epsilon t. So substitute in this factor. So e power epsilon t, e power minus epsilon t. If we solve it, we will be getting e power minus bt into c plus d plus epsilon t into c minus d. This is the general solution for the damped oscillation in the condition in which b square is equal to omega square. Right? So we will move on to the second one, the underdamping condition. So in the underdamping condition, that b square is less than omega square. That means the frequency of the oscillating system is ahead of the resistive force. So b square is greater than omega square. In that equation, b square minus omega square will become negative. So if it is in negative, it will be very difficult to solve it, or the equation will become complicated. So to solve that, we are considering omega square minus b square to be a positive quantity. So we will be taking minus sign outside. So square root of minus 1 will be I. So you can write n I. Okay, or in we can write it. So this is the how we have to rewrite this equation. And at the same time, here the underdamping condition in which the body is oscillating, the system is oscillating for a time period t with a diminishing amplitude. What is the diminishing amplitude? E power minus bt. How far the amplitude reduces? With the factor of minus b, that is nothing but the resistive force. So what is the coefficient of resistive force? Alpha. So we have to determine what is alpha and what is b. So once we determine these two, the equation is solved. So now we have to solve what is the displacement equation for a forced vibration when b square is is less than omega square. You got it. The third case is what? We are going to derive the displacement equation of a damped oscillating system for which the resistive force is less than the frequency of oscillating system. So let us consider the general equation for an oscillating system, what we derive. So x is equal to x naught by 2, etc. So in which I am going to substitute the factor of square root of b square minus omega square with the in value. So wherever square root of b square minus omega square is there, I am going to replace it by in. So here second term, the third term, and also the fourth term. So these are the places in which we are replacing square root of b square minus omega square by in. Power minus bt is common for this term as well as this term. So I am going to take the e power minus bt outside. So we'll be getting 1 plus b by in into e power int. Okay. Similarly, 1 minus b by in into e power minus int. Is it clear? So these two factors, the second equation reaches like this. So e power minus bt will be taken as common, and we are rewriting this equation like this. So afterwards, x naught by 2 e power minus bt. So these two terms, when it multiplied with here and also when it multiplied with here, similarly when this one is multiplied with here and this one is multiplied with here. So e power int plus e power minus int, I am writing it together. Then b by in with the factor of e power int, b by in with the factor of e power minus int will be written separately. So b by in will be taken as common outside. So we are writing x by x naught by 2 into e power minus bt e power int plus e power minus int plus b by in e power int minus e power minus int. By using the Euler's theorem, e power plus int is equal to cos nt plus I sin nt, and e power minus int is equal to cos nt minus I sin nt. By substituting these two values in the previous equation, you will be getting cos nt plus I sin nt, that is e power plus int, and cos nt minus I sin nt, that is for e power minus I sin nt. So these are the two factors we are substituting it. Then when we substitute these things, so minus int plus int, minus and plus int will get cancelled. Similarly, minus cos nt plus cos nt will get cancelled. So you will be getting 2 cos nt and similarly 2i sin nt. So these two will be there. So then the 2 will be taken as common outside, so that this 2 and this 2 and this 2 will get cancelled. Similarly, this I and I will get cancelled. So after getting cancelled, just multiply with the whole, take a n term common outside. So when you take n outside, so x naught by n e power minus bt, you have to multiply here. So n cos nt and b sin nt. So I am going to replace n is equal to alpha sin phi and b is equal to alpha cos phi. So n I am going to substitute here, and similarly b I am going to substitute here. So I will get alpha sin phi cos nt plus alpha cos phi sin nt. So these two equations I will get it like this: alpha sin phi cos nt plus alpha cos phi sin nt. So alpha I am going to take it outside as a common term. So this alpha and this alpha will be taken outside. So x naught by n alpha e power minus bt sin nt plus 1, that is sin a cos b plus cos a sin b. So sin of a plus b. Then n is equal to alpha sin phi, b is equal to alpha cos phi. When I divide these two, so n by b, alpha will get cancelled. So sin by cos you will get tan. So tan inverse is equal to phi is equal to tan inverse of n by b. Here x naught n alpha, x naught by n into alpha will become a. So a is equal to x naught n by alpha, phi is equal to tan inverse of a. This is the general solution for the damped oscillating system when b is less than omega. So this is your amplitude of the oscillating system. What happened to the amplitude of the oscillating system? It decreases with respect to the factor of e power minus bt. Sin nt plus phi is nothing but the sinusoidal waveform. So the amplitude decreases with the factor of minus bt. So this is the general solution for underdamped condition. Thank you.